Hi everyone. In this lecture, I will talk about building an intelligent world with a cycle of IoT, cloud, big data, AI, and IoT. All right? Okay, this outline of the lecture. The first, I'll talk about cyber physical systems, CPS, and CPS is an O2O Space Revolution, and also it's a convergence of AI and ICT, right? I'll look at CPS from two different views. Then I will introduce basic concepts for major components of CPS, which include IoT, cloud computing, big data, artificial intelligence, and I will talk about a cycle of IoT Cloud, Big Data, AI, and IoT. Then I will discuss the main topic, which is building an intelligent world from the view of intelligent digital transformation and convergence of AI and ICT for intelligent service. In the part 1 of this lecture, I will cover CPS, IoT, and cloud computing. And in the part 2, I will cover the rest, okay? Cyber Physical System, CPS, refers to all the technologies enabling computerized resources and physical objects to interact together in a coordinated, reliable, and continuous manner for performing multiple given tasks. So CPS may combine hardware and software from physical, biology, engineering, and information technologies. So here, communication, control, and information are key elements to form CPS, cyber physical systems. All right? It is an O2O, online to offline space revolution. Basically, cyberspace and the physical space are combined with communication via connection, wireless communications, and computing via intelligence with artificial intelligence, and control, automation to realize intelligent digital transformation, right? We have cyberspace, it's also called online. Physical space is called offline. These two spaces are connected. All the physical things are monitored and the status is reported to cyberspace, and the cyberspace manipulated the accumulated data and some artificial intelligence functions are implemented, and the result will be sent to actuator in the physical world, right? So here, in between online and offline, the reality can be extended via augmented reality, virtual reality, and mixed reality, right? This is indeed O2O Space Revolution, right? So, in the O2O Space Revolution, everything in the physical world are virtualized, right? And all the virtualized entities are stored in cyberspace, right? So IoT service can be created from objects to virtual things, right? And between physical world and the cyber world, basically IoT services are created for observation and control, okay? It's also virtual world and physical world, right? Again, everything in the physical world are virtualized, and the virtualized objects are stored in the cyberspace, all right? So it forms cyber twin, right? The physical world and cyber world. Everything in the physical world are virtualized and stored in the cyber world to form twins of the object, right? So CPS is also called cyber twins. All right, network elements in CPS architecture. In the physical world, things are virtualized, and virtualized objects are transported to the cyber world via various wireless communication technologies and wireless networks, right? And the received information from physical world are transported over the internet, and the data is stored over the cloud and stored under the big data umbrella, right? Then this accumulated big data is manipulated to create intelligent IoT service, right? This is overall network elements in CPS architecture. CPS is a technology convergence of artificial intelligence and ICT producing data, right? The core ICT components for producing data include IoT for generating data and wireless communications for ubiquitous connectivity environment by connecting IoT devices, and cloud for storing data, and big data for analyzing data. And these ICT functions should be functionally supported well in a balanced way to utilize artificial intelligence for intelligent O2O services, right? So this indeed, this CPS is a technology convergence of AI and ICT. I call this system as an intelligent ICT, IICT, right? Now, here's an example of technology convergence of ICT and artificial intelligence.
Good morning, Jarvis.
Good morning, Mark.
I talked to Jarvis using this app I built. It uses artificial intelligence to understand me and figure out what to do. Fresh shirt!
Fire in the hole.
Hell yeah.
As a takeaway, I'd probably just caution everyone to understand that perhaps you should use big data to make your small decisions and use your gut to make the big decisions.
Now, this convergence of AI and ICT makes continuous cycle for improvement. From plan, do, check, adjust, and plan again. Do collect data through IoT and check through big data analytics and adjust and plan by artificial intelligence. It's based on data-based learning, right? This is a continuous cycle for improvement and for more intelligent service. All right, let's go over key ICT components generating data. They include IoT, cloud, and big data. For IoT, the number of billions of connected devices is an indicator of IoT. The connectivity is just an enabler, but real value of IoT is on data, right? Which provides business insights and data-driven economy. And cloud offers everything as a service, business model for IoT and big data. For big data, over the cloud is data collection. It's one of the main concerns, and IoT can play an important roles for data collection and data sharing. For big data, data is nothing without real business value insights, right? So someone say, IoT is a king, big data is a queen, and cloud is a palace. Cloud is a place to store big data, and data is collected throughout IoT, right? Now, let's look at each individual components of ICT generating data. First, IoT, Internet of Things. IoT is a system of interrelated computing devices mechanical and digital machines provided with unique identifiers, so UIDs, and the ability to transfer data over a network without requiring human-to-human or human-to-computer interaction, right? So between internet and everything in the physical world are communicating through this IoT. Okay.
Cloud computing is the on-demand delivery of IT resources via the internet, with pay-as-you-go pricing. Instead of buying, owning, and maintaining physical data centers and servers, you can access technology services such as computing power, storage, and databases on an as-needed basis from a cloud provider like Amazon Web Services. Organizations of every type, size, and industry are using the cloud for a wide variety of use cases, such as data backup, disaster recovery, email, virtual desktops, software development and testing, big data analytics, and customer-facing web applications. For example, healthcare companies are using the cloud to develop more personalized treatments for patients. Financial services companies are using the cloud to power real-time fraud detection and prevention. And video game makers are using the cloud to deliver online games to millions of players around the world. With cloud computing, your business can become more agile, reduce costs, instantly scale, and deploy globally in minutes. Cloud computing gives you instant access to a broad range of technologies, so you can innovate faster and build nearly anything you can imagine. From infrastructure services such as compute, storage, and databases, to Internet of Things, machine learning, data analytics, and much more. You can deploy technology services in a matter of minutes and get from idea to implementation several orders of magnitude faster than before. This gives you the freedom to experiment and test new ideas to differentiate customer experiences and transform your business, such as adding machine learning and intelligence to your applications in order to personalize experiences for your customers and improve their engagement. You don't need to make large upfront investments in hardware and overpay for capacity you don't use. Instead, you can trade capital expense for variable expense and only pay for IT as you consume it. With cloud computing, you access resources from the cloud in real time, as they're needed. You can scale these resources up and down to grow or shrink capacity instantly as your business needs change. Cloud computing also makes it easy to expand to new regions and deploy globally in minutes. For example, Amazon Web Services has infrastructure all over the world, so you're able to deploy your application in multiple physical locations in just a few clicks. Putting applications in closer proximity to end users reduces latency and improves their experience. No matter your location, size, or industry, the cloud frees you from managing infrastructure and data centers, so you can focus on what matters most to your business.
Now, cloud computing. Cloud computing is the foundation of the IoT. IoT and cloud computing deliver powerful innovation that will continue to alter how we interact with our devices and with one another, and change how we store, manage, and consume information. All right? So, the cloud computing is the backbone of everything IoT has to offer, right? So, cloud and IoT are tied together to make IoT service function, okay? Now, let's look at motivation for cloud computing. In case of real-world estimates for capacity, server capacity, average server utilization is 5 to 20%, and peak workload exceeds this average by factors of 2 to 10. Now, users provision servers for the peak, right? The peak loads may occur based on the time of day or based on other factors. For example, photo sharing after the holidays, drop ad within 2 weeks of start of term, and so on. So, under these circumstances, we need for growth of efficient provisioning demand, right? So we have clear motivation for cloud computing. Now, let's look at issues of traditional network capacity provisioning model. Network capacity is provisioned based on planned forecast, right? So if internet capacity is expected to have this level, right? And we provision network resources accordingly. Then network traffic, data traffic is extremely fluctuating sometimes, right? So sometimes you need more capacity, more bandwidth, right, to transport more data, right? So if you provision at this level, your provisioned capacity is not enough. So obviously you underestimated system utilization, right? Which results in under-provision, right? So you will lose some subscribers. Therefore, you will lose the revenue associated with the lost subscribers. How about this case? You forecast this level capacity, right? But actually, you didn't need that much capacity for the subscribers, for the traffic, real traffic. Then obviously you overestimated system utilization, right? Which resulted in low utilization. So in this case, this much capacity is wasting. This is surplus capacity. So this is unused capacity, right? It's idle capacity, but you put investment for this capacity provisioning, right? So you need for growth of efficient provisioning demand to avoid under and over provisioning, right? This is also clear motivation for cloud computing. Cloud computing has been actively promoted since the bubble burst of the internet industry in early 2000 here, right? Let me explain what happened here, right? This figure shows 140 years history of telecommunication, right? And 140 years since telephone was invented, it's divided into 3 stages in terms of services, right? Voice service era for more than 110 years. And during this period of time, it wasn't difficult to forecast the expected traffic. So network capacity can be provisioned based on the clear planning, right? There's no problem. But after internet was invented, the internet data traffic grew up significantly, right? Since internet was invented in late 1980s, right? So since then, we are living in internet services era, right? Up until now. And now we are moving into era of intelligent ICT service. Now, in data traffic, internet traffic era, the internet traffic is very busty, right? So it's extremely difficult to forecast the capacity, right? So capacity planning is very difficult because of nature of data traffic. Data traffic is very busty, right? So ISPs put investment for enough capacity, right? For the data traffic growth. But on the other hand, the subscribers don't pay enough for this investment, right? So the gap between this investment level and revenue from subscribers become huge, right? So economic bubble burst occurred in early 2000, right? So ISPs looked for other way to compromise this gap instead of putting continuous investment on the capacity, right? So the problem is to reduce filling up this gap is really challenging. We have to increase revenue, reduce cost, improve experiences, new value creation through ICT convergence. Now, for this requirement, all the network resources need to be virtualized so that the surplus capacity can be utilized effectively, right? So cloud computing is the foundation to fill up the gap, right? So cloud computing was paid a lot of attention since this bubble burst, right? So the objective of cloud computing is dynamically provision resources, right? So pay only for what you use, and fast agile deployment and monthly payment plans, pay as you go, pay as you use, and requires less in-house staff and reduces the cost of infrastructure, right? So this is great for startups, the barriers to entry, right? For startups. So in traditional provisioning mechanism, there might be a lot of surplus capacities, unused capacity. At the same time, there might be underestimated area for the actual traffic. So in this case, the revenue and the subscribers can be lost. With cloud computing, provisioning can be made based on actual utilization, right? So the cloud computing provides this optimization, right? Now, let me introduce definition of cloud computing from NIST. Cloud computing is a model for enabling convenient, on-demand network access to a shared pool of configurable computing resources. For example, networks, servers, storage, applications, and services that can be rapidly provisioned and released with minimal management effort or service provider interaction. Okay? All right, essentials for cloud computing. Cloud computing is utility computing, which means cloud services are controlled and monitored by the cloud provider through a pay-per-use business model, just like electricity and water at your home, right? An ideal cloud computing platform is efficient in its use of resources, scalable, elastic, self-managing, highly available and accessible, and interoperable and portable, right? Properties of cloud computing. First, resource efficiency, elasticity, which means computing resources can be rapidly and elastically provisioned to scale up and released to scale down based on consumers' demand. And self-managing services, and accessible and highly available, right? Features of cloud computing. Great availability of resources, on-demand self-service, easy maintenance, large network access, availability, automatic system, economical, security, pay as you go, right? These are fantastic features of cloud computing. All right, there are 4 primary cloud deployment models: public cloud, private cloud, community cloud, and hybrid cloud. All right. Based on spectrum of cloud users, there are three types of service models, right? First, infrastructure as a service, and platform as a service, and software as a service. For infrastructure as a service, in general, network architects are involved. Platform as a service, application developers use this service, and end users in general use software as a service, right? As you move up from infrastructure to software, value visibility to end users, right? Now, let's look at three types of service models based on-premises computing stack. On-premise computing stack has network, storage, servers, and virtualization. Virtualization concept is extremely important in cloud computing, right? All the resources are virtualized basically, and anyone can use the surplus capacity as long as they pay for it, right? And on top of this, you have OS, middleware, runtime, data application, right? On top of virtualization, you have software stacks, right? Software functions. Below virtualization, you have hardware. Okay, so infrastructure as a service, IaaS, right? So service provider offers infrastructure below virtualization, right? So basically they use virtualization pool, right, to support this surplus hardware capacity. Now, platform as a service, PaaS, right? And the service providers support up to this level: OS, middleware, and runtime. And the developers can add their application apps on top of this platform, right? And software as a service, SaaS, service providers provide everything from infrastructure to software, okay? Now, let's look at virtualization for infrastructure as a service. Virtualization is the abstraction of logical resources away from underlying physical resources. And the virtualization is a creation of a virtual rather than actual, the version of something such as an operating system, a server, a storage device, or network resources, right? So at the virtualization level, all the network resources are encapsulated and abstracted, right? So that surplus capacity can be found and provided. All right, this is high-level architecture for virtualization. The lowest level, you have network and the storage hardware. And you have virtual infrastructure. On top of this, you can have multiple virtual machines, right? each virtual machine has operating system and application software. All right. All right. This slide shows comparison between traditional hardware stack and virtualized stack. Traditional stack, each hardware is dedicated to operating system, and on top of this, multiple applications can be added. On the virtualized stack, between hardware and multiple virtual machines, hypervisor layer is created. So the hypervisor manages OS as a virtual machines, enabling multiple OS to share the same physical hardware, right? So this same hardware can be shared by multiple virtual machines. This slide shows comparison of server virtualization and network virtualization. For the server virtualization, this physical hardware can be shared by many different virtual machines with server hypervisor, right? For network virtualization, you have physical network resource and you have network virtualization platform. And on top of this network virtualization platform, multiple virtual networks can use same hardware resources, right? All right. This slide also shows comparison of server virtualization and network virtualization. For server virtualization, run multiple virtual servers. On a physical server, right? So each virtual machine has illusion it's running as a physical server. Network virtualization run multiple virtual networks on a physical network, right? And each virtual network has illusion it's running as a physical network. Now, with network virtualization, you can build logical topology for different virtual networks on top of physical infrastructure, right? Now, with network virtualization, you can have multiple slices for different service requirement, right? So you have a network virtualization pool, and this pool can be sliced for multiple service requirement, right? This concept, this slicing concept, is extremely important concept for 5G network, right? So without having this virtualization concept, you cannot build 5G network. So the network virtualization is that important. Network virtualization is key background technology for 5G. All right, as a summary of virtualization, let's look at benefits of virtualization. You can have security, economical, and flexible transfer of data, and flexible operations, and eliminates the risk of system failure, right? This all can be managed at a common virtual pool. Types of virtualization. We have a desktop virtualization, application virtualization, server virtualization, storage virtualization, and network virtualization, right? And we looked at network virtualization and server virtualization, which were very commonly used and very important, okay? All right. Спасибо. Thank you.